Good afternoon, everyone. In the previous presentations, we have discussed about photoelectric effect as well as Compton effect. In this particular presentation, we are going to discuss few problems on photoelectric effect, and probably in the next presentation, we'll discuss few problems on the Compton effect. So these problems have been asked in the various competitive exams, for example, JEE, IIT-JAM, etc. So we'll try to solve these problems, and we'll basically focus on the approach. So if you see the first problem, it says that the sodium and copper have work functions of 2.3 electron volts and 4.5 electron volts respectively. Then the ratio of their threshold wavelength will be. It's a pretty straightforward. Used a different color. It's a pretty straightforward problem. You know what is the value of threshold wavelength? The value of threshold wavelength is Hc over psi. This Hc is a constant and this psi is basically the work function. So we understand that this lambda Th is inversely proportional to the work function. So it means that the threshold wavelength of sodium over threshold wavelength of copper will be equal to the work function of copper over the work function of sodium, because obviously we have the inverse relation. So if we put the values, the threshold, the work function of copper is 4.5 electron volts and this is 2.3 electron volts, it's close to 2:1. So this is the ratio of the threshold wavelength. This is how you do the first problem. So let's move on to the second problem. In second problem, it says that the stopping potential V0 as a function of frequency is shown. So you know that this is a very standard plot. We have discussed about this plot in detail in the theory. If you remember, I can just write down the equation. So you remember this V0 is H over E times mu minus psi over E. So this is basically the equation of the line which is depicted here. So we have to basically calculate the work function of sodium. You know, we have already discussed in the previous lecture that this particular thing is the threshold frequency. If you look at it carefully, because this 4, not this particular thing, but this 4 is basically the threshold frequency. That is, this is the minimum frequency which is required to trigger the photoelectric effect. If the particular frequency is less than the threshold frequency, obviously the photoelectric effect will not happen. This is what the graph tells us. So we have to calculate the work function. Let us see what we have got. So you have this mu naught as 4 into 10 raised to the power 14 hertz. You see, into 14 hertz. So this is just to done the scaling. So this mu naught, which is the threshold frequency, is given. Mu naught is equal to 4 into 10 raised to the power 14 hertz. If you remember the expression for lambda Th, the expression for lambda Th is Hc over psi. If I ask you to calculate the threshold frequency, use lambda naught for threshold wavelength. If I ask you to calculate this threshold frequency, obviously this threshold frequency will be C over the lambda naught. And what is C over lambda naught? From here, it is psi over h. So this psi, or basically the work function, is mu naught times capital H. And this is what we have to calculate, the work function. Now if you just substitute the values, this mu naught is 4 into 10 raised to the power 14 hertz. Into this h is 6.63 into 10 raised to the power minus 34. Yeah. And to convert this expression into electron volts, we are dividing it by 1.6 into 10 raised to the power minus 19. And this value comes out to be close to, if you calculate, 1.657 electron volts. So this is how you do this particular problem. We were given a plot and we were asked to calculate the work function. Now let's look at the next problem. In this problem, it is said that in a photoelectric effect, the threshold wavelength is 380 nanometers The wavelength of incident radiation is 260 nanometers. The maximum kinetic energy of the electrons is. It's also a very simple problem. You know what is the expression for maximum kinetic energy? You can write maximum. I'll just drop it because it's very understood that it's maximum kinetic energy. This kinetic energy is E minus psi. If you remember what this E is, this E is hc over lambda I for incident, minus, what is this psi? Psi is hc over lambda th. If you just basically take this particular thing common, hc, so be 1 over lambda I, that is incident, minus 1 over lambda th. If you just substitute the value 1 over lambda I, incident radiation is 1 over 260 minus 1 over lambda th is 380, and we are given that we have to use the value of hc as 1237 electron volts. So it is 1237 electron volts. If you basically take the LCM, you have 260 into 380. This is 380 minus 260. You have to basically solve this expression, and when you solve this expression, you get the value to be approximately 1.50 electron volts. Okay, standard result, standard expression, and you have to use this particular expression. Okay, so this is how you do the third problem. Let's move on to the next problem. It says that threshold frequency for a metal surface corresponds to the energy of 6.2 electron volts, and the stopping potential for the radiation incident on the surface is 5 electron volts. The incident radiation lies in which band? Okay, so it's also a pretty straightforward problem. So it says that threshold frequency for a metal surface corresponds to the energy. It means that threshold frequency for a metal surface, it corresponds to energy, means that we are given the work function, because threshold frequency only corresponds to the work function. Because threshold frequency is the minimum frequency which is required to trigger the photoelectric effect. So it obviously corresponds to the work function. So we are given work function of the metal surface, and this is given to be 6.2 electron volts. This is the work function. And we are given the stopping potential. V0 is given to us as 5 electron volts. Now we have to calculate the wavelength, because there is only one way through which we can know that in which particular band the incident radiation lies, and that is to calculate the wavelength. There doesn't seem to be any direct relation between the given data and the wavelength, but there is a relation between this particular data with the energy of the incident radiation. And we know, if we know the energy, we have a simple relation, E is equal to hc over lambda. This hc is a constant. We can easily get the wavelength, and through the wavelength we can guess, or we can be pretty sure about what is the band in which this particular radiation lies. So this psi is given to us, V0 is given to us. Let us write the standard expression. You have kinetic energy, obviously maximum, is equal to E minus the work function. We have to get the energy, so this energy is equal to psi plus kinetic energy. If you recall, this kinetic energy maximum corresponds to EV0. If you remember our discussion, we said that even the electron with the maximum kinetic energy should not be able to reach the anode. So all of its kinetic energy will get converted into the potential energy EV0. So basically, this V0 corresponds to kinetic energy maximum. This kinetic energy maximum must exactly be equal to EV0. So this, instead of this kinetic energy, we'll write V0. If you add it, this value of this is 6.2 electron volts, plus V0 is given to us as 5 electron volts. This is equal to 11.2 electron volts. This is the value of the energy of the incident radiation. I hope you get the logic of this kinetic energy, how I have written this equal to the value of V0, because if you remember, we said in the experimental setup that even the electron with the maximum kinetic energy should not be able to reach the anode. So therefore all the kinetic energy that the electron had gets converted into the potential energy, and therefore it does not have any further energy so that it can reach the anode. So that's why we are writing this kinetic energy to be equal to the stopping potential. Yeah. So this becomes 11.2 electron volts, and now we can just use this expression lambda is equal to hc over lambda is equal to hc over E, and this hc is 1240 eV over the energy that we use is 11.2 electron volts. Cancel this out. This becomes 110.71 nm. So this becomes close to 1107.1 Armstrong. And you remember, and if you look at your textbooks, you will find that this is the region of UV. So the radiation lies in the UV region. Yeah. Let's move on. Let's move on to the next problem. We have question number 5. It says that a photoelectric surface is illuminated by a monochromatic light of wavelength lambda and lambda by 2. If the maximum kinetic energy of emitted photoelectrons in the second case is 3 times that the first case, the work function of the metal is. So it is given, we are given 2 situations. Let me try to draw it straight. Yeah, we are given 2 situations. You have an electromagnetic beam in both cases, okay, and it is given that the wavelength is lambda, the wavelength is lambda by 2. In this case, the electron gets emitted, the electron gets emitted with some kinetic energy. The maximum kinetic energy of emitted photon in the second case is 3 times that in the first case. It means if we assume that the kinetic energy is k here, so obviously the kinetic energy is 3k here. Yeah. So we have to calculate the work function of the surface. Now obviously we use the basic photoelectric expression, the photoelectric equation, and that is, we know that kinetic energy maximum is E minus psi. Okay. Now if we calculate what is this energy E, it will be kinetic energy plus psi. This kinetic energy, or this E basically is hc over lambda is equal to k plus psi. This is we can write this particular thing for the first expression, because we know that since the wavelength is lambda, so the energy is hc over lambda. This kinetic energy is k. The maximum kinetic energy is k. So we have write k plus this some work function psi. Now for the second case, this is the equation 1. Oh, we are not left with space, no issues. For the second case, we have if we write the same particular equation, we know that E is equal to kinetic energy plus psi. This is hc over lambda by 2 is equal to 3k plus psi. This is equation number 2. Now we have to basically get this okay, so we have to basically get this expression regarding this psi. So we need to eliminate this kinetic energy, this k here, because once we eliminate this kinetic energy, we will get the value of psi. So if you look carefully, I am multiplying equation number 1 with 3, because then this becomes 3k, and I am subtracting it with 2. So therefore this becomes 3k, and when I subtract it, so this basically vanishes. So I am multiplying 1 by 3, so I get 3 hc lambda by 2. Oh no, sorry. I have to multiply this equation. Yeah. So basically becomes 3 hc over lambda, and I'm subtracting it with this. This 2 comes up. This is minus 2 hc over lambda. this is 3k and 3k gets cancelled. This becomes 3 psi minus psi. So this becomes hc over lambda is equal to 2 psi. Therefore this psi becomes hc over 2 lambda. This is the value of the work function. Okay, now let's move on to the next problem. We have in photoelectric effect, in the photoelectric experiment, lambda of incident radiation is changed from 300 nanometers to 400 nanometers. Find the decrease in the stopping potential. Okay, so the lambda of incident radiation is changed from 300 to 400. Find the decrease in the stopping potential. Okay. So let's write our standard equation. So you have kinetic energy is equal to energy of incident radiation minus psi. You can write energy equal to k plus psi, and I'm writing this energy is hc over lambda. This is equal to kinetic energy plus psi. Now let's denote. Okay, so let's write for this 300 nanometers. So we get hc over lambda 1. This lambda 1 is equal to 300 nanometers. We'll put the expression when we'll put this value lambda 1 equal to 300 when we get the final expression. So this hc over lambda 1 becomes equal to the kinetic energy k plus this psi or this work function. So we can write this work function, or no, maybe, yeah, we write this psi, the work function, plus we write the kinetic energy in the form of the stopping potential. This is EV1. So this corresponds to the stopping potential for this lambda 1, which corresponds to 300 nanometers. Similarly, we'll write for 400 nanometers. So this is hc over lambda 2. This is equal to psi plus EV2, and this V2 corresponds to the stopping potential when we take lambda equal to 400. So now using these equations, we'll find the decrease in the stopping potential. The decrease in the stopping potential is obviously V1 minus V2. So if we use this particular equation, we eliminate psi from here, we get hc over E 1 upon lambda 1 minus 1 upon lambda 2. This is equal to V1 minus V2, which is the decrease in the stopping potential. So obviously if you subtract this equation, you will get this thing. Okay, so this if you subtract this from this equation, we get EV1 minus EV2, psi cancels, you send this E to the other side, this is what you get. Now we have been asked that to use this hc over E as 1240. So we use 1240, 1 upon lambda 1, which is 300, minus 1 upon lambda 2, which is 400, and this is the delta V, which is the change in the wavelength. We take the LCM, 1240 into, this is 400 minus 300 is 100 over 300 into 400. Whatever is this, you may calculate, and I think this will come out to be this 0 and this 0 cancels off. Sorry, just a second. And since there is no space left, you can basically calculate this expression. It will come out to be in some electron volts. Okay. Let us move on to the next problem, which will be the last problem, and it's an interesting one. So in this particular problem, since the magnetic field is involved, it becomes an interesting problem. So you have to mix your knowledge of photoelectric effect as well as the knowledge of magnetism. So in this particular question, we have been asked that there is a beam of 450 nanometers light is incident on a metal having work function 2 electron volts and placed in a magnetic field. The most energetic electron emitted perpendicular to the field are bent in a circular arc of radius 20 centimeters. So you have to basically find the magnetic field. Now you know that when there is a charged particle and when it moves in a circle, you know what is the expression for the radius. Since the value of radius is also given, so you can get a hint that we are going to use that expression, and since that expression also contains magnetic field, so you must have got the hint. So this value of this radius, you know, it is mv over qb. If you must have gone through a little bit of magnetism, you know this is the value, And this value, to be honest, is not very difficult to derive. You can just use this particular equation. You know that this QVB, that is the force on a charged particle when it is kept in a magnetic field. This provides the necessary centripetal force, and this V and this V cancels off. You have R to be equal to mv over qb. Remember, this radius, this expression for radius is only valid when the magnetic field is perpendicular to the when you have kept magnetic field which is perpendicular to the direction in which the charged particle is moving. So this is the expression. Now we have to calculate this value of B, the magnetic field. So this value of this magnetic field B is, you have mv over q times r. The value of q, since it's an electron, you know the value of q is 1.6 into 10 raised to the power minus 19 coulombs. The value of r is given to us already, 20 centimeters. So we have to basically compute this mv, the mass times velocity, which is nothing but the momentum. Okay, which is nothing but the momentum. So it should be clear to us that all the rest of the information which is provided to us, that this lambda or this work function will be used to calculate basically this mass times velocity, which will be the momentum. Now we know this mass times velocity momentum is related to kinetic energy. Yeah, we know that this kinetic energy is equal to p square over 2m. So basically this p will be nothing but 2mk. This will be the value of linear momentum. Do we know how to calculate this kinetic energy? Of course we do, using the Einstein's photoelectric equation. Once we know the kinetic energy, we'll be able to calculate this momentum, and once we know this momentum, we'll just basically put this in the star expression and we will get the value of the magnetic field. So this kinetic energy, using the same, our very old friend, the Einstein's photoelectric equation, is kinetic energy is E minus the work function. This energy we can write hc over lambda minus the work function psi. You know what is the value of this hc? You know, you should also remember the value of this hc. It is very, very useful in the competitive exams. It is 1240 eV Nm, because h is constant and c is also constant. You divide it by lambda, it is given to be 450 nanometers, minus the work function is given to be 2 electron volts. If you calculate this kinetic energy, this will be equal to, the kinetic energy will be equal to 2.75 electron volts minus 2 electron volts. This will be 0.75 electron volts. Now, to convert this electron volts in joules, we multiply this 0.75 by 1.6 into 10 raised to the power. Because now, why are we doing this? In the previous questions, we didn't convert this electron volts into the joules, because now since the magnetic field is involved, and you know, magnetic field, the unit of magnetic field is Tesla. So we want everything in the standard units. So basically, we multiply this electron volts by minus 19, and we get the kinetic energy as 1.2 into 10 raised to the power minus 19. Yeah, minus 19 joules. This is what you get. This is the kinetic energy. And now, as I just discussed, once we know the kinetic energy, we can easily get the value of linear momentum if we put the value of kinetic energy in this particular expression. So this linear momentum P is under root 2 times the mass, which is 9.1 to 10 raised to the power minus 31, into the kinetic energy, which is 1.2 into 10 raised to the power minus 19, and you get the value of linear momentum as 4.67 into 10 raised to the power minus 25 kgs meter per second. You know, that's why we converted this value of kinetic energy in joules, because we want everything to be in the standard units. We want momentum in the kg meter per second unit. Okay, so now since we have momentum, it is very easy. We need to just substitute the value of this mass times velocity. You know, this magnetic field, if you want to calculate, it's mass times velocity over q times r. This mass times velocity is nothing but the momentum. So we get the value of magnetic field as 4.67 into 10 raised to the power minus 25 kgs meter per second over q times r. Q is 1.6 into 10 raised to the power minus 19 times r. This is the value of r. Where if r is 20 centimeters, we should convert it in meters. So that will be 0.20 meters. 0.20. If we calculate this particular expression, the value of magnetic field is 1.46 into 10 raised to the power minus 5 Teslas. This is the value of magnetic field. So we solved this particular problem. Now that is it for today. In the next presentation, we'll try to do some problems on the Compton effect. Thank you.